Okay, uh, let's start the session. Okay, am I audible? Okay, let's start the session. So, welcome back to the ninth live session of Solar Energy Engineering and Technology. Myself, Soumya Tiwari. I'm PhD scholar at Department of Sustainable Energy Engineering at Kanpur. So, last time someone asked me to recommend a book other than this Shukhatme and Naik Solar Energy book. So, I forgot to tell you the last time, but the book I'm writing it in the chat box. So the other book that you can refer to is Solar Engineering of Thermal Processes. Okay. Okay. This is a book by Duffy and Beckman. So the writers are Johnny Duffy and William Beckman. Okay. So this is the book. You can get this book online also. The PDF of this book online also. So if someone want to solve and get better understanding of uh, this particular course, they can refer to this book also. So I've written the name of the book and the author in the chat box. Okay, so let's start the today's session. So in this session we'll discuss about the solar air heaters. So okay, solar air heaters are another application of solar thermal devices where your solar energy is utilized to heat the air, and then this heated air at certain temperature is utilized for several application. Now, so air is a heat transfer medium here, which directly absorbs your incoming solar radiation and used for application. So several application like drying of agricultural product, industrial process heat, space heating are the several examples of these applications. So if you see the construction of a solar air heater, then um, you know that there is some absorbing plate, right? Uh, and uh, a cover, and there is a back plate. Okay, so this is the back plate, the blue one. In between your air is flowing. This absorber plate is covered by some glass material, or as we have discussed earlier also, and the air is flowing between these two plates, the absorber plate and your back plate. So this configuration might depend might be different for different type of solar air heater, but the whole understanding is that there is a two plate, the back plate and your absorber plate, through which your air is passing. And if the solar radiation is falling on this cover glass and then goes to this absorber plate where this plate is being heated, and as the air passes through the space between these two plates, it is then heated by due to the heat generated from this absorber plate. So that is the general understanding. Now, so here the specification of typical solar air heater is also given. The solar air area requirement to 2 meters square, the glass thickness 4 to 5 mm. It could be of plastic also. The main objective of this cover is basically to uh, avoid the dust sedimenting on the this absorber plate, right? Now, so at the this back plate, what we don't want to get our heat loss, right? So we provide insulation at this back, and and along the side walls also. So for that we use mineral wool or grass wool, and this whole setup is kept in a sheet metal box. Now, so the advantages of this solar air heater is basically your corrosion and leakage problem is not there. Also, as compared to liquid flat plate collector, right? So here only we are using air. Um, also this point is also important because in a liquid, if you are going for say water below 0 degrees Celsius, if we want to do the application of this liquid flat plate collector, the basically it will freeze, right? So the choking can also occur. So but in the case of air, there is no such problem, so you can also use it below 0 degrees Celsius. But the disadvantage is, since we are using air, so the heat transfer coefficient is very low, so the efficiency is very low for this solar air heater. And also we have to use a large volume of fluid to basically get our desired useful heat gain. So for that, what we can do is, additional thing that we can incorporate in the design of solar air heater is, we can roughen the surface or we can use the fence, right, to increase the heat transfer. So there are various type of solar air heaters, with fins, without fins, absorber plate, roughened to give this V-shaped absorber plate. And depending on where air is flowing, it is it between the your basically, if two covers are there, is the air is flowing from one cover gap to second cover gap, and then from absorber plate to back plate, depending on um, uh, different application we are required. Okay, so this is the performance analysis of solar air heater. We can see the how the solar radiation are coming. Some are being reflected, and then some are being transmitted, and then absorbed by the absorber plate, and then some of them are re-radiated the long wavelength. And this when this plate get heated, the absorption from this plate to the flowing air occurs, and some losses also occur from the backside and due to some convection. And at last we get some amount of useful energy by the transporting medium, which is around 60%, right? So only 60% of the incoming solar radiation are used, say, if a given basically at this given condition as shown here, right? So this is the derivation. I will not go deep into the derivation. What I will do is, I will highlight the important point. So we assume the some important assumptions are there that you need to basically remember, and then also some importance formulas. So uh, this formula, right? How to calculate this HR? Uh, okay, heat transfer coefficient efficient for the radiation thing. So this formula is important. Okay, assuming that there is negligible difference in heat transfer coefficient for both plate. The both plate we are talking about is the absorber plate and the back plate. Okay, and then um, your this effective heat transfer coefficient between absorber plate and air. This formula is also important. Okay, so you need to remember this formula. If you'll see the lectures of the sir uploaded on the swam site, you can easily understand how this derivation are derived. I'm just telling you what formula you need to remember to solve the numerical problem. Okay, so this effective heat transfer coefficient formula you need to remember. And then okay, this collector efficiency factor, this is also another important formula. Okay, so and based on this you can calculate your Q useful. And now you have collector heat removal factor, so you can see there are very analogy between the flat plate collector, the liquid flat plate collector, and solar air heater, because the terms here like collector efficiency factor, the collector heat removal factor are same as we have seen in the liquid flat plate collector, right? So the formulas are also quite similar. if you want to remember those formula. So you can see your you can this formula is also remember, so these two formula. Okay, so right. And now if you want to calculate the pressure drop. Okay, so for a fully developed flow in a smooth surface, your duct, the pressure drop can be calculated using this dimensionless this friction factor value. Okay, and to so you need to remember this formula. This might be given in the problem your problem statement only, but this is the most widely used Nusselt number formula for this fully developed region for a smooth surface duct. So this you need to remember. And you know that if you calculate Re, Reynolds number, then you'll be needing this equivalent diameter, and the equivalent diameter formula is 4 into your cross sectional area of the duct divided by your wetted perimeter. So these three formula, knowing this F friction factor value, you can easily calculate your pressure drop. Your pressure drop formula, your delta P value will be your 4 FLV square by 2D. So if you are from mechanical background, you are aware of how this all comes into picture. Basically, you need to remember this, how to calculate friction factor and how to calculate this pressure drop. So we will also solve one numerical problem based on all this. Uh, Basically, what derivation we have seen. So to understand better how in real condition these all parameters are calculated, performance parameter are calculated for solar air heater. Okay, so okay, so um, so from here, several types of solar air heaters are explained. As I have told, two pass air heater. So this is your bottom plate provided with the insulation, right? And this is your absorber plate. So the now the airflow is somewhat, you're first flowing the air from between the cover and your absorber plate, so that the this cover temperature also sometimes it increases. So to basically does not get overheat of this cover temperature, because the higher will be the cover temperature, higher will be the losses also, right, to the atmosphere. Because this say TC temperature is there for cover and Ta temperature is of ambient, higher will this temperature, more will be losses. So it's basically beneficial also, because your cover temperature is now in this type of flow, your cover temperature is also decreased, and your uh, air is also getting preheated, right, before coming to this between this absorber plate and the your bottom plate. So you can see the better up to an inlet air temperature difference of 20 degrees Celsius. um, this is another configuration where the air is flown between this uh, there are two covers, right, and then your absorber plate. So not so your air is being preheated in this second cover and your absorber plate. So the temperature difference is around 50 degrees Celsius now. So basically it's how these configurations suggest how we can increase the efficiency, right, by minimizing the heat loss to the atmosphere. So you can see the efficiency of these type of collector are measured to be 10 to 15% higher than the conventional your air heaters. Now if you use a porous medium in between your absorber plate and your bottom plate, so this porous medium, what does it porous medium does it basically in this porous medium, your surface area for heat transfer increases in a given volume, right? So basically your heat transfer increases and your efficiency also increases. So you can see that efficiency of around 70%, 10 to 20% higher than that of collector without the porous medium can be achieved in this type of um, configuration of solar air heater. Some other design are matrix, plastic, transparent air heater. Um, I think these are basically are using a matrix here. Matrix are made up by stacking wire, like wire screen meshes. So wired meshes are there, right? Or a slit expanded metallic foil, and through this, um, uh, basically these are used to increase the turbulence, so better mixing will be there, right? Better mixing will be there, uniform temperature will be there, more basically heat transfer will be there, so thereby the efficiency will also increase, higher collector efficiency will be there. um, so this is one type of configuration. And then this is similar to two pass air heater but with a matrix here. So you can go for a cheaper version of the solar aerator by using a plastic, right? So you are using some flexible plastic seat, and and the see the absorber here could be a porous black textile or polyester. You can paint it black and then increase the absorption, right? So these are all the different configuration that you can go by yourself. What is next important thing is this unglazed transpired collector on a vertical wall. So you might have seen this similar design on the wall somewhere. So basically, how this works is you have this wall, and here is your perforated absorber plate. Okay, so this plate. So it's perforated. Perforated means air can pass through it, right? So what happens is as so due to your say some on some wall your solar rays are falling, and this wall temperature is going to increase, right? So as air passes through on the side of this wall, the air gets heated, and this is then the blower is sucking up the air in the upward direction also, and due to density difference also it will rise, right? So then this hot air is used to basically at a particular air conditioning or at given temperature or moisture content, then it is fed to a given space. So this is a very typical space heating application in a cold countries. It can be also used for the crop drying, and uh, so the this planum depth ranges from 5 to 30 centimeter. So let's see a numerical on this. So the question is, the temperature rise T of air through a vertical south facing unglazed transpired collector is found to satisfy the following empirical relation. So the relation is I think the relation is T equal to, I think this was the relation, right? Okay, change in temperature equal to, this is IT plus 3. From an air flow rate of 36 meter cube per hour per meter square of UTC, IT is the total solar radiation incident on UTC in watt per meter square. T is in degrees Celsius. Assuming this relation to be valid, calculate the efficiency of a vertical south facing UTC for the following data. The location is given. So the longitude and latitude are given. Phi and L is given. The date is given. You can calculate N from here, and you can calculate the declination angle. Our angle is given. Omega is given. Air flow rate is given in meter cube. So it's basically volume flow rate is given in meter cube per hour per meter square of UTC. Global solar radiation on horizontal surface. So what is given is Ig is given, right? Global. And the diffuse solar radiation on horizontal surface. So Id is given. D is for diffuse. And the reflectivity of the ground is given. Rho of ground is given, right? So in this particular problem, what has been asked is, say a wall is there, a south facing wall is there, vertical wall is there, in which you are using this unglazed transpired collector. Then what will be the efficiency of this UTC for a given location at a given condition, right? So if you want to calculate the efficiency, the general understanding is efficiency is equal to your output upon input, right? So here output is your utilized heat, QU, and your input energy is your incoming solar radiation on this wall, right? which will be your IT into A. A is the area of this wall, right? So if you write QU, utilize heat, it will be m dot Cp delta T. You know that how much temperature, how much energy is required to raise the temperature through delta T temperature, right? So now we'll see what parameters we have uh, uh, in this efficiency equation and what we don't have. So we have value of air flow rate in uh, it basically a volume flow rate is given. We can change it into mass flow rate, right? Mass flow rate per area. So what is given, it is given volume flow rate per area, because if you see the unit, it's in meter cube per hour per meter square, right? So the actual thing that is given in the question is volume flow rate per unit area, right? If you want to change it mass flow rate, then you know that mass is equal to, okay, so what we'll do is, um, basically it's given in 36 meter cube per hour per meter square. We'll multiply it by density. Mass equal to volume into density of air, and the density of air we can use, and then we can get this mass flow rate per area, per unit area. You can get the value of m dot upon A, right? Hope you got this, right? How to basically change from meter cube to your kg, volume flow rate to mass flow rate. Now, you know the value of Cp, you know the value of Ig and Id, but you know what will be the IT, the total incident, solar incident falling on this vertical plate. So, first, you know the global and the diffuse. You can calculate the beam or direct radiation falling on this vertical wall, which will be your global minus diffuse. That will be the your beam radiation or the direct radiation, right? And we know the IT, the total uh, solar flux falling on this wall will be given by this equation that we have already seen earlier, right? So what we need to calculate is, you know, the IB, ID and IB plus ID, right? Your global diffuse and beam radiation. You need to calculate this R for beam radiation, R for diffuse radiation, and an R for reflection, right? So we also know the formula for these three things, right? We have already studied earlier. So RB will be cos theta upon cos theta z. This is for horizontal and this is for tilted at beta angle solar air heater. And RD, you know that 1 plus cos beta by 2, and RR is equal to reflectivity. Reflectivity is here from given for the ground, right? Or reflectivity for the surrounding surface, right? So it will be reflectivity into 1 minus cos beta by 2. Now we'll see what angles we have right now. So the wall here is vertical, right? So the wall here is vertical. So the beta angle will be 90-degree, right? Omega is already given in the question. It is 15-degree. Phi is already given in the question. 28.58. It's 28-degree, 35 seconds. So you can calculate in degree, right? Now the date is given. Date is the December 10. Right, for December 10 we can get the number of days from January 1, which will be 344, and for n value 344 we can calculate this declination angle, right? We have already done this type of calculation many times. So we are seeing how the application of all those calculation that we have studied way back in the initial lectures, right? So we now know all the angle. We know the beta, we know omega, we know phi, we know delta, right? You can put back into this equation, this RB equation, and we can get the value of RB, which will be, I think, 1.295. Okay. Similarly, you can calculate RD for diffuse. So 1 plus cos beta, beta will be 90-degree. It will come to zero point 0.5, and your rho is zero point 0.2 reflectivity, and your beta is 90. You can get the RR value. So from that you can calculate the total flux falling on the vertical wall. From IT, what you can uh, calculate is, there is a relation given already in the question to calculate the change in temperature uh, as a factor of IT, right? So you can calculate delta t from this particular relation already given in the question. So we have calculated all the unknown value for the efficiency formula that we have explored here. So we can put all this value back into the equation. So to get your efficiency is 41.88%. So I hope there is a similar question in the your assignment question also for this week. So if you have any doubt in this question, you can write in the chat box or you can raise your hand. Any doubt in this question? Okay. So I hope there is this question is clear. Okay. Now, um, testing of a solar air heater. So, as we have already seen the testing of a liquid flat plate collector. Similarly, uh, we have a testing of solar air heater also. So, this is your solar air heater. Uh, with some help of blower and mass flow controller and some air conditioning apparatus, we can do the testing of the solar air heater. So here you can see, um, uh, with the help of blower and this mass flow meter or rotameter, at a given condition of the input of the air, with the help of this air reconditioning apparatus, we can feed the air into this solar air heater. We can measure the inlet temperature, and we can also measure the outlet temperature after this thorough mixing used by this mixing vanes, and we can measure the pressure drop across the solar air heater, and then the reconditioning may occur, and this process may continue for several um, value of mass flow rate to get the basically efficiency curve, right? So so what value we can actually measure during the testing is your inlet temperature, fluid inlet temperature, fluid outlet temperature, the pressure drop we can measure, right? The mass flow rate we can measure, right? So mass flow rate we can measure from here. uh, your inlet and outlet temperature we can measure, the pressure drop temperature, the pressure drop across the solar air heater, these value we can actually measure in a during the testing of solar air heater. Based on this value, what we do is we plot a temperature between your efficiency and your this factor. So Ta is your ambient, It is your total incident flux onto the solar air heater, and Tf bar is your basically average temperature of the absorber plates we are talking about. Absorber plate and your bottom plate, right? So, in if you remember in flat plate collector, your liquid flat plate collector, we have just done for one mass flow rate, and we have predicted the behavior or performance of a solar air heater. Because in that case, your heat transfer coefficient for liquid is very high, right? So if you change the mass flow rate, there will not be much difference in the performance of a liquid flat plate collector. But in case of solar air heater, we are using air, right? So the heat transfer coefficient for that is very low. So what we do is we basically plot this performance curve for various mass flow rates for your efficiency, right? To basically calculate its performance. How it is done will be well explained by this particular problem. Okay, so if you see this problem, the efficiency curve, this is if you can, solar air heater, this is curve obtained after the testing. Okay, so here we can see here is your efficiency, and on the x-axis we have this particular parameter, particular term. Okay, so this is called efficiency curve. Efficiency curve shown in figure 1 are obtained by solar for a solar heater which length and L1 and L2 are given, right, which is tested over a range of flow rate varying from 25 to 200 kg per hour. So the flow rate that we see here is 25 to 200 kg per hour. Find the efficiency which would be obtained and the corresponding mass flow rate. So what we have been asked is the efficiency and the mass flow rate if the air heater is used under the following condition. Your inlet air temperature is given, right? Inlet is given, the outlet temperature is given, the ambient temperature is given, and your solar flux incident on the collector face is IT is given, right, in 950, which is 950 watt per meter square. So how to calculate efficiency and mass flow rate for this particular condition? So it's a sort of iterative method, hit and trial method. What we do is, uh, we know that um, the inlet and outlet temperature, right? You can calculate the mean temperature. So the TF bar. So sorry for the thing that I have explained here. The TF bar is basically average temperature for the fluid. So the average temperature will be for the inlet and outlet, right? So the you can calculate the TF bar here because TF inlet temperature and the outlet air temperature is already given in the question, which will come to be 66 degrees Celsius. Now we have to calculate this term. Okay, so TF bar minus TA upon IT. We already do the ambient temperature 26 degrees Celsius and we know the value of IT. Note that the unit here, it is in degrees Celsius meter square per kilowatt. Okay, so it's in degrees Celsius, right, per meter square, so it per kilowatt. So you have to the unit for IT will be used in kilowatt. So note that this calculation mistake doesn't happen. So you have to always use in, you have to see for what is given in the graph, what unit is given in the graph. So okay, so it will be 0.95, so we will get 40 degrees Celsius meter square per kilowatt. So corresponding to x value of 40 degrees Celsius meter square per kilowatt, what we can do is we can extend this x value onto the curve and see what is the efficiency for this particular x value, what will be the y value for this particular one curve. So say if we will start by taking the lowest mass flow rate value, which will be 25 kg per hour. So if you'll basically calculate it from the graph, your for this 25 kg per hour mass flow rate, your efficiency will be 24.2. Okay, so this will be 24.2%. So what we are trying to do is here is we will for this efficiency we will back calculate the mass flow rate value and see whether the mass flow rate that we have assumed and what we are getting, it is matching or not. If it is not matching, then this is not the basically condition for whatever condition is given in the question. So we have to then do again hit and trial method for another mass flow rate value. So that is the basic approach for this particular question. So say we have assumed for the first hit and trial method is for say 25 kg per hour. We know the efficiency value, we can calculate the q useful value, right? Heat useful we can calculate, we already know the value of IT, and we already know the area of your collector, which is given 1.2 into 0.9, right? You can calculate q useful. From q useful, what we can do is we know that qu equal to m dot cp delta t, right? From here we can calculate this mass flow rate value. So if we'll calculate this mass flow rate value, it will come to be 44.38 kg per hour. So if we see compare these two values, the assumed value was 25 and the value we are getting for after calculation was 44.38 kg per hour. So this is not the correct answer. So what we'll do is we'll increase the now mass flow rate. Say we are going for a 50 kg per hour. We'll repeat the same process. we'll see for 40 x value, we will basically see on this 50 kg per hour curve what will be the value of y, that is the efficiency. And from that we'll calculate the q useful, and from there we can calculate the your mass flow rate value. We'll see that the mass flow rate that we assumed was 50 kg per hour, and the value we are getting after calculation was 51.354 kg per hour. So it's not exact, but it's similar, right? We are approaching towards our answer. So what the next value that we have assumed was 51.4 kg per hour, and see whether we are getting for this value we are getting our close answer or not. So we'll again repeat the process, and if you'll see that, so for 51.4 kg per hour, note that for 51 you only know the curves direct value for 50 and so 25, 50 and 100. So for 51.2 51.4 there will be one more line similar to this, right? So this will be say for 51.4 kg per hour. So how we'll calculate this efficiency value? For that you have to interpolate, right? Interpolate between this 50 and 100. So we know the say for this particular x we know the value of y for 50 and 100. So for change in for 1.4 kg per hour change we can interpolate the value and get the value of efficiency, right, for this particular thing. So that you have to calculate from the graph. And first so we'll after calculating the efficiency we can repeat all the processes, and you can calculate the mass flow rate value, and we can see that the value are quite similar, right? So this will be your particular mass flow rate that we are aiming for, and this will be your particular efficiency. Okay, so I hope this the this question, the solar air heater performance efficiency curve question is clear. um, okay, so this is the similar question. I think the values are also same. Okay, so only the inlet, outlet, and temperature are different here. So the basically the approach to these type of question will be similar to what we have just seen here in this question. So I'll not re-explain this particular question. If you have any doubt in the question, please let me know right now. You can unmute yourself and ask. Okay, so moving on to the next part of this solar air heater. So how solar drying for agricultural products. Okay, so how this solar air heater are used for drying of agricultural products. So you know it's a very most common and oldest application of solar energy for drying purpose, right? So basically design of this solar dryer are based on empirical and semi-empirical data than the in theoretical design, and basically used for small scale your crop drying thing or small scale industrial production, right? So the basic principle, as you know, that we have some crop or say something that has to be dried with some moisture content, right? So basically your heat energy from the solar rays are utilized to basically evaporate this moisture content from this particular sample, and then that is the so basically what we are doing is we are changing the phase of the water from your liquid to your uh, basically steam, right? So note that uh, theoretical question will be mainly asked from this solar drying of agricultural product. So you need to know the all the facts and basically terms used here. So free what is free water, what is bound moisture. So free water is basically your unbound water content within the sample. So and the bound moisture is basically what is held or trapped between the capillaries of the basically your sample we are talking about. So this makes the material hygroscopic and non-hygroscopic, depending on we have whether we have bond moisture or the free moisture. So the moisture content can be expressed in on the based of dry or wet basis. So if you are going for wet basis, we are basically calculating the moisture content with respect to your wet material weight. Okay, and if you are going for dry basis, so we are only using the mass of your dry solid, and here we are calculating the mass of water with respect to your whole dry plus as well as your wet content. Okay, so on wet basis your agricultural product moisture content is mainly calculated. On dry basis your all the mathematical calculation are done, right? So now coming to drying rate. So drying rate depend on various parameter, like what is the temperature of the product, what is its moisture content, what is your ambient condition, what is your temperature, what is your relative humidity, what is the velocity we are using for the your drying air, right? So if you see that this is the curve that we get for if we try to calculate drying rate with respect to time. So this basically explain different phases of drying that basically undergoes. So initially some time is required to heat that basically your uh, whatever your drying material to a particular temperature, your drying temperature. And then in phase 1 there is a constant rate drying, and then this rate decreases as the moisture content goes on decreasing in your material. And um, basically this drying rate decreases further in this phase 3, where the if there are some left moisture inside the product, that also takes place basically get removed through capillary action and diffusion, and then your drying finally stop at point this 3. So okay, water activity is another important term. So, what is water activity? If you want to understand its significance, then for every product, say food or agriculture product, there should be some minimum amount of basically water or that needs to be there for a particular microorganism to prevail in that particular product. Okay, so we are trying to calculate this water activity uh, regarding that particular basically application only, at which moisture content or at which the water content this microorganism stop growing. So it is given by your, I think it's alpha water content. Water activity is given by alpha W, which is your partial pressure of water solution to partial pressure of pure water at the same temperature. Okay, so majority of bacteria grows at alpha W value of 0.85. Mold and yeast grows about uh, 0.61, and your fungi grows at more moisture content of zero point 0.7. Now, what is equilibrium moisture content? So if this is your material with some moisture, if the your vapor pressure exerted by the moisture in this product is equal to the vapor pressure, and this is your surrounding, right? So if it equal to the vapor pressure of this nearby ambient air, then that moisture content is known as your equilibrium moisture content. And this is the absorption isotherm. So when your moisture content is there, your water activity increases, that means your moisture content increases, right? So during your uh, air drying, solar drying, your this uh, basically desorption curves is there. So there is some um, what hysteresis involved, right? So this is your hysteresis curve for the Jobson isotherm. So I'll not go into detail, much more detail. You can go back into the lecture and watch this. So another important thing is your solar chimney power plant. So what we have is a tall chimney is there, right? You can see this. This is the actual image. This is a your very tall chimney, right? A circular greenhouse with a transparent cover. This a metal frame to hold the greenhouse and a fan and generator unit. So this is your fan and generator unit, which is, so what happens is, as the air sunlight passes through this transparent cover, uh, the air trapped inside this greenhouse get heated, right? So due to natural convection, what occur will, this air will rise upward, right? And we are also using some this fan also, right? Fan and generator unit, so it will suck the air, and as this air will flow, it will move this turbine, and then your electricity or mechanical energy you basically will be used to, mechanical energy will be converted into your electrical energy for power generation. So these are the typical solar chimney power plant, how the construction or is there for solar chimney power plant. So this is the specification given for a pilot plant in Spain. So the the numerical will be based on this formula also. Okay, for this solar air chimneys. So the conversion efficiency of this solar air chimneys are very low. The maximum conversion efficiency is given by this formula. You need to remember this formula. The maximum efficiency is given by GH upon CPTA, where you know that G is your gravitation constant 9.81, H is your height of the chimney tower, CP is your specific heat, and TA is your temperature of the ambient air. Now let's see a numerical based on this particular solar air chimney. So, with following assumption and given data, calculate the maximum possible conversion efficiency. What has been asked is maximum possible conversion efficiency obtainable with the chimney. Also, estimate the efficiency of the plant as a whole and the daily electrical output in a typical summer month of uh, given your incident flux is given, right? What else is given? The height of chimney is given. Solar collection area of the greenhouse is given. Your area is given. CP is given. CP is your 1005 joule per kg per Kelvin. Ambient temperature is given. Assuming that the turbine generator set converts only 50% out of the maximum available energy into electrical energy. And the collection efficiency of greenhouse is also 25%. So we already know the formula for the maximum efficiency, maximum possible conversion efficiency for a given solar air chimney, which is given by GH upon CPTA. Your G is 9.81, your height is given 300, your CP value is 1005 joule per kg per Kelvin, and your ambient temperature is 305. You can calculate the maximum conversion efficiency, which will come 0.0096. In percentage, it will be 0.96%. So you can see that how less how much lower value is there for this the efficiency value is there for the solar air chimneys. It's only 0.96%. That is maximum efficiency that we can gain from this solar air heater, right? If you want to calculate the efficiency of plant as a whole, so in plant what we have is we have, if you remember this, we have this uh, greenhouse, right? And we have this turbine fan and generator unit. So what's given in the question is the collector efficiency of greenhouse is 25% and turbine generator set efficiency is 50% only. So whatever maximum available energy is there, it is converting only 50% of that. So the overall uh, conversion efficiency will be uh, basically this is your value that we got, the maximum value, but only 50%, 25% is actually collection efficiency of greenhouse, and 50% is for the turbine generator set. So your value will be 0.0012, and if you want to calculate it percentage, it will be only 0.12%. So the actual overall efficiency as a whole of the whole plant will be actually 0.12%. It's very low, right? And if you want to calculate the daily electrical output, so the daily electrical output of the plant will be, so you know the efficiency, so it's basically q useful upon your input is your incident into your area, right? So your, in term of output, if you say electrical output, we can use this efficiency term, right? So it will be overall efficiency into your it into a. So your I is your 6.5 kilowatt hour per meter square, and your area is given this much meter square. So you can multiply it, you can see that 390 kilowatt hour is the daily electrical output of this plant. Okay. Okay, so this is all for the content that has been taught in the lectures for the week, I think 9 week 9. So what I will do is, now I will show some question, and will I ask you all to write the answer into the chat box. Okay, so this is the first question. I will read it aloud. So the heat transfer coefficient in case of solar air heater is improved by which of these factors? Okay, let's see this question. So a heat transfer coefficient in case of solar air heater. So, so this is your solar air heater. Say this is your cover. This is your absorber plate, and this is your back plate. Say with some insulation. Okay. Now, if you want to increase the heat transfer coefficient, what things we can do? Providing roughened surface or longitudinal fins in the airflow passes. That is true. If what we do is, if we'll see the cross sectional area, if we rub this surface, the absorber plate surface, right, and or if we include some fin, right. So some fin, if you are including some fin in this basically cross sectional area, longitudinal fin, then your heat transfer coefficient will be increased. So this is correct. Uh, so this option A will be correct. Increasing the mass flow rate will not affect the heat transfer coefficient, right? And the cleaning of glazing surfaces will also not increase the your heat transfer coefficient. So the correct answer will be the option A only. By providing the roughened surface or the longitudinal fins in the airflow passes, what we can do is we can increase the heat transfer coefficient for your solar air heaters. Now the next question is, the solar air heater is more effective and economical compared with liquid flat plate collector due to which of these options? Okay, we got one answer which is option D. So that is the correct option, answer D also, because in solar air heater we are using air, and so what, we don't have freezing problem, we don't have corrosion problem as compared to the liquid that we are using in liquid flat plate collector, and there is also less leakage problem, no leakage problem. So the correct option will be the option D. Now the next question is, uh, when the vapor pressure exerted by the moisture of the drying product equals the vapor pressure of the nearby ambient air, the moisture content is termed as, is it a bound moisture, free moisture, unbound moisture, or equilibrium moisture? Okay, so it's not so this question holds that like the theoretical part from the your drawing of the crops and agriculture product or drawing of any material, you need to basically understand what those terms or means, and you have to remember that for theoretical question from this solar air rating. Okay, so this I have explained in this live session also. So say if you are talking about any material kept in ambient condition, so the moisture content of this drying product when equals to the vapor pressure exerted by this moisture of this drying product when equal to the vapor pressure of the nearby ambient air, then that moisture content is known as equilibrium your moisture. Okay, so the correct option will be option D. The unbound moisture is basically trapped in the capillaries, and the free moisture is the moisture other than the capillaries which can be easily removed, right? So the correct option for this question will be the option D, that is the equilibrium moisture. So the next question is, the solar air collector is mostly operated under natural, forced, turbulent, or none of this. Which mode? Okay, we have got one answer, option A. Okay, if you remember, we have seen in most of the setup, say if this is your wall, this is your perforated wall, and if the air is coming from here, if you remember, there are some fans used here, right? Fans or blower used here, or if you remember uh, the the solar air tower, right? So so this is your greenhouse, and here your fan generator system is there. So in most of the application, if you'll see, uh, the solar air collector are mainly in the forced mode. Okay, so because we are using some external means, right? So this fans and blowers. So the correct option will be forced mode. Okay. Now, the next question is, the outlet air temperature of solar air collector. How it depend on the mass flow rate? So, does it depend on mass flow rate? If yes, then how? Whether it increase or decrease if we decrease the mass flow rate? Okay, if you'll let's see this question also. If you see the Q useful, it will be the m dot cp delta t, right? The delta t is so temperature of fluid at output minus temperature of fluid at inlet, outlet and inlet, right? So uh, if we'll see mass flow rate equal to qu upon, or we can say, right, let's write in term of uh, okay, so okay, so okay, let's, so your tf naught will be, what tf naught will be your qu upon m dot cp, right? And plus tfi, right? So you can see by this relation also, if you increase the mass flow rate, then your uh, or if you'll decrease your mass flow rate, your then your tf naught will be increased, right? Your outlet air temperature will increase. And you can also understand basically this, that if your mass flow rate is great, so in a given time there is a lot of mass to be heated, so your outlet fluid uh, temperature will be lower. So if you decrease the mass flow rate, your outlet fluid temperature will increase, right? So the correct option will be option B. Now, okay, this is the question for solar chimney plant. So okay, let's first solve this question and then we can go back to the solving the lengthy question. Okay, so the solar chimney plant of 280-meter height is installed in collection area of 45,000 square meter. The temperature of the ambient air is given 30 degrees Celsius. Specific heat of air is given 1005 joule per kg per degree Kelvin. Solar energy available in the location is 6.2 kilowatt hour per square meter. Assume the turbine generator set converts only 55% of the maximum available energy into electrical energy, and collection efficiency of greenhouse is 24%. What will the maximum possible conversion efficiency for the solar chimney? So it's just a one formula question solution basically. Please calculate this particular solution and then you can write your answer in the chat box. Okay, let's solve this question. So what's given in question is a solar chimney plant is there. Its height is given. So the height is 280 meter. The collection area is given. So the area is given to be 45,000 meter square. The temperature of the ambient is given in degree Celsius. So it's 30 degrees Celsius. Okay. Or in Kelvin, what we can write is 273 plus 30, which will be equal to your 303 Kelvin. Okay. The specific heat of air is given. The CP value is given 1005 joule per kg per Kelvin. The solar available energy is given at the particular location. So the I value is given, which is 6.2 kilowatt hour per meter square. What else is given is the turbine, your turbine generator efficiency is given 55%, and your collection efficiency of greenhouse is given 24%. Now what has been asked is the maximum possible conversion efficiency for the solar chimney. So we know the for maximum conversion efficiency, we know the formula, it's G into H upon your CP value into your temperature of the your ambient, right? So it will be 9.81. Height is your 280, right? CP value is 1005 in joule per kg per Kelvin, and your ambient temperature is 303 Kelvin, right? So it's in Kelvin and Kelvin, right? So if you solve this, your maximum efficiency will come to be your 0.00902. In percentage, if you want to write, it will be your 0.902%. Okay. So your correct answer will be 0.90, which will be option B. Okay. Now, the second part is to calculate the overall efficiency of the plant. So if you want to calculate the overall efficiency, what we know is your overall efficiency will be the maximum efficiency into your efficiency for your turbine generator set, right? Into your efficiency of your greenhouse collection efficiency, right? So it will be your 0.902 divided by 100, right? Into your uh, turbine generator efficiency and into your collector efficiency. So if you will solve this, it will come to be 0.00119067. Okay, so this will be in percentage, you can write it as 0.119%. Okay, so it will be the option A. Now the next part is the daily electrical output of the solar chimney plant in kilowatt hour. Okay, so we know the overall efficiency, right? We know that it is equal to your uh, electrical output, right? Upon your input. Your input is your solar, your thermal input, right? Your electrical output will be your overall efficiency into your input. Input is your incoming solar flux onto your area, right? This is your input energy, right? So it will be equal to your 0.119, right? Into your I value is 6.2 kilowatt hour per meter square, right? And your area is 45,000, right? So it's 45,000 meter square. So in kilowatt hour, if you'll calculate this, your output will come to be 332.198 kilowatt hour. Okay, so this will be your answer, option C. Okay, hope this question is clear. Okay, moving on to the next part. Okay, so this is the question. This is the question based on uh, how to calculate a performance parameter of a conventional solar air heater. Okay, so um, this question will basically clear all your doubt how to uh, basically calculate the performance parameter in of a solar air heater in a actual application scenarios. So what I will do is I will solve this question because it's a very lengthy question. It will take some time. So I will request you all to solve side by side, and let's see this question. So the question is, calculate the performance of a conventional solar air heater with the following data. So what data is given? The length of collector. So say this is your solar air heater. Okay. This is your absorber plate. This is your black back plate with some insulation, right? And this is your cover, right? This is your cover, this is your absorber plate, and this is your back plate with some insulation. Now the length of collector is given. The length is given to be 2.1 meter, and the width of the collector is 1.1 meter. Okay. The length of the absorber plate, this is the absorber plate, right? So the length is given 2 meter, and this length is given 1 meter. Okay. Now the spacing between the absorber plate and the bottom plate. So this value is given to be 1.5 centimeter. Okay, this is given in centimeter. The air flow rate. So some air is flowing, right? So the mass flow rate is given to be 200 kg per hour at a air inlet temperature of 50 degrees Celsius. Your ambient temperature is given to 20 degrees Celsius, and your incident solar flux. So your incident solar flux is given 950 watt per meter square. Now your transmittivity absorptivity factor average value is already given, so it's given 0.85, and top loss coefficient is given. So your top loss coefficient is given 6.2 watt per meter square Kelvin. Bottom loss coefficient is given, which is zero point 0.8 watt per meter square Kelvin, and your the emissivity for your plate and your bottom plate is given to be 0.95. So what we have been asked to calculate is the performance of this conventional solar air heater. So let's see how to uh, practically understand what's actually going on in this solar air heater. Okay, so with some assumption, we'll see the derivation. We have some assumption that we are ignoring the side loss, and your temperature is not varying across the absorber plate and the bottom plate. So considering all those application, your sorry assumptions, what we'll do is first we'll calculate what is the heat transfer coefficient for fluid, for the absorber plate and your bottom plate also. So what will calculate is your heat transfer coefficient for fluid, for your plate and your back plate. Okay, so your inlet fluid temperature is 50 degrees Celsius. Assume that your assuming that your fluid, your average or mean temperature is 55 degrees Celsius, because you need to calculate all the dimensionless number. You need to have some a mean temperature on which you will calculate the basically your parameters for your air, right? So say for 55 degrees Celsius, your density will be 1.077 kg per meter cube. Your Cp value will be 1 point, it's 0.005. We are writing in kilojoule per kg Kelvin, right? Then your mu will be required, right? Viscosity 19.85 into 10 to power minus 6 Newton second per meter square. And your thermal conductivity, that will be your 0.0287 watt per meter Kelvin. Now first we'll see whether your flow is fully developed in this solar air heater or not. For that, what we need to know is your equivalent diameter, your length upon equivalent diameter, right? That value we have to see whether it's what is its value, right? So if you remember the derivation, first we need to calculate the equivalent diameter. So equivalent diameter will be your 4 into your cross sectional area, right? cross cross sectional area of your duct upon your wetted perimeter, right? So it will be 4 into your cross sectional area is your this, right? So it will be 1 into this is in centimeter, right? So you will write 1.015, and your wetted perimeter will be your, so your wetted perimeter is basically this, right? This whole thing. So it will be 2 into 1 plus 0.015. So this equivalent diameter DE will come to be your this will be 0.0296 meter. Okay, so we will calculate L1 by DE value. So L1 is your if you'll see, your L1 is your 2 meter, right? So this, the length of the duct is 2 meter, the equivalent diameter is your 0.0296. This will come to be your 68. So this value 68 is greater than 30, right? So what does this ratio shows that the flow is your fully developed flow. Okay, so we are having fully developed flow in our air duct, right? What? So first, because if you see that the formula, the empirical relation that we have seen is for the fully developed flow in a smooth surface duct, right? So first we need to ensure that the at a given condition whether our flow is fully developed or not. So that we have checked. Ki your fully flow is your fully developed flow, right? Now the uh, air flow rate is given. So from air flow rate, we know the area, we can calculate the air velocity, average air velocity, right? So if we'll calculate the average air velocity, what it will be your, uh, this is your mass flow rate, 200 kg per hour. So if we'll convert it into using this, if you basically calculate the velocity, it will be your 200 kg, and hour you can write 3600, right? So it will be kg per second. Then if we divide by the density of the air, the density of air was 0.77 kg per meter cube. And if it, so this will be your um, this will be your volume, right? Now if you divide by the area, you can get the uh, this is basically your volume flow rate. If you divide by the area, we'll get the air velocity, right? So your area was 1 into 0.015. This is in meter square, right? So here it will be meter. This will cancel and it will be the value for average air velocity that we will get will be 3.439 meter per second, right? So we have calculated the average velocity in the dark. Now what we can see is what is the Reynolds number, because to calculate the Nusselt number and know whether the flow is laminar or turbulent, you need to know this Reynolds number, and with the help of this Reynolds number we can calculate the Nusselt number, and from there we can calculate the heat transfer coefficient, right? If you remember, we have solved the similar question in previous classes also. So Reynolds number, you know the formula, it's rho v, the equivalent diameter upon your viscosity, right? So we know the density, it's 1.077 into velocity, we know 3.439. Equivalent diameter we also know, d value is this 0.0296 upon your mu value is 19.85, 19.85 into 10 to power minus 6. Your Reynolds number will come to be 5515. So clearly this is the turbulent flow, right? This is a turbulent flow. Now assuming that we have a smooth surface of the duct for a fully developed, so we have a fully developed turbulent flow, right? We know the Nusselt number formula. Nusselt number empirical relation is, it is 0.05 no, 158. It's 0.0158. Reynolds number to the power 0.8. Okay. So if we'll put the value, it will be 0.0158. Reynolds number is your 5515 to the power 0.8. This value will get Nusselt number is equal to this will come to be 15.56. Okay, and this is basically your HL by K, right? Or this is your H, heat transfer coefficient, into your equivalent diameter upon your thermal conductivity, right? So from here you can calculate the HFL, which will be Nusselt number into thermal conductivity upon your equivalent diameter. So your HF for your plate or your HF for your back plate will be equal to, Nusselt number is 15.56 into your thermal conductivity is 0.0287. Okay, so it's 0.0287 upon your D is your 0.0296, right? 0.0296. So we get your value to be 15.08 watt per meter square per Kelvin. So we have calculated this heat transfer coefficient for fluid uh, for a plate, absorber plate and your back plate. Now if you remember the formulas, uh, then your to calculate the heat transfer coefficient for radiative heat transfer, if you remember the formula, it is sigma, your 1 by epsilon for the absorber plate upon 1 by epsilon for the back plate minus 1 into your temperature for mean temperature for your plate plus mean temperature for your back plate into TPM square plus TBM square. Okay, so assuming that your there's not much, if you see the derivation also, we'll see the similar basically approach. So we'll see that your temperature, basically your temperature between difference temperature difference between your absorber plate and back plate is sort of less than 10 Kelvin, the difference. So we are assuming that your TPM, okay, your plate mean temperature and your uh, bottom plate temperature mean temperature is equal, and it's equal to your uh, fluid mean temperature. This seems a logical assumption because if there is not much difference between temperature of this absorber plate and back plate, we can assume that this temperature is equal and equal to the mean temperature of the air flowing between this plate, right? So if we'll put this assumption into this equation, the HR equation will be your sigma upon 1 by epsilon p upon 1 by epsilon b minus 1. This will be TFM plus TFM. This will be 2 TFM into your, this will be 2 TFM square, right? So it will be sigma into 4 into your TFM fluid mean to power 3 upon 1 by epsilon p plus 1 by epsilon b minus 1. Okay, so we'll put the values into this equation. So it sigma is your Boltzmann's constant, 5.67 into 10 power minus 8 into your 4 into your fluid temperature, mean temperature that we have assumed is your 55 degrees Celsius, right? So it will be your uh, 273 plus 55 cube upon your epsilon, your emissivity value for plate and your back plate is 0.95, right? So it will be 0.95 plus 1 by 0.95 minus 1. So I'll get HR value to be, I think this will come to 7.24. Okay, so okay, so this will be 7.24 watt per meter square Kelvin. So we know the value of HR, we know the value of HR, and we know the value of HFP and HFB. So if you remember the formula, we can calculate the equivalent heat transfer coefficient, right? So so let me go back to the derivation so you can correlate. So what we have done till now is where we have calculated this uh, heat transfer coefficient for both plate, and we have calculated this HR value, right? Now what we can do is we can calculate this effective heat transfer coefficient between the absorber plate and the air. So if we'll see the effective heat transfer coefficient, if you remember the formula is your HFP. So this is your HFP plus HR into your HFB upon HR plus HFB. So this is B, right? So it SFP is your, for plate heat transfer coefficient is 15.08, 15.08 plus HR is 7.24 into the back plate value is also same, and this is 7.24 plus 15.08, right? So this will, the equivalent heat transfer coefficient between your absorber plate and your back plate we have now calculated. This will be 9.97 watt per meter square Kelvin. Okay. Now, using this, what we can calculate is your collector efficiency factor, right? So your collector efficiency factor will be, which is F dash. The formula Okay, so for the formula for that is 1 plus overall heat loss your coefficient and your equivalent heat transfer coefficient. So this f dash will be equal to 1 plus ul is what your top loss coefficient was 6.2 and the bottom loss coefficient was 0.8, and we have ignored the side loss coefficient, right? Assume that the side loss coefficient is negligible. So it will be your 6.2 plus zero point 0.8 divided by your equivalent heat transfer coefficient was 19.97. So it will be 19.97. So this will be 1 plus 7 upon 19.97 whole inverse. So this will come, the value will be 0.740. Okay. So the value will be 0.740. Now, uh, if you want to calculate the FR, right? So FR, if you remember the formula, MCP upon ULAP into 1 minus e to power minus of f dash into this inverse of this, right? So it will be m dot cp ul ap, right? We will calculate this m dot cp value. So this value will be mass, basically mass flow rate is your 200 kg per hour, right? So it will be kg per second, right? Into your cp value is 1.005. Uh, so it's in joule, sorry, in kilojoule. So in joule it will be multiplied by 1000, and your overall heat loss coefficient is this 6.2 plus zero point 0.8. So this will be 7, right? Into your area for plate, that will be 1 into 2, right? 1 meter cross 2 meter was your area of the absorber plate. So this value will be, I think this value will come 3.488. So we'll put this value into this equation to get the another performance parameter for a solar air heater, right? So this will be 3.488 into 1 minus e to power minus uh, f dash is your 0.740, right? And this is 3.488. 3.488. When you will solve this, your FR value will be, so your FR value will be 0.675. So we have calculated the F dash value 0.740 and FR value. From that, what we can calculate now, your useful heat gain. So your useful heat gain, we know the formula, it will be FR into area of the plate into your incoming solar flux minus your loss. Loss is your overall heat loss coefficient into your uh, in term of fluid inlet temperature minus your ambient temperature. Okay, this is your loss term, and this is your the incoming flux, right? So we already know all the values. What we can do is FR value is your 0.675. Area of your plate is 1 into 2 absorber plate. The incoming solar flux. So what's given in the question is your incoming your solar flux incident on the collector phase is 950 watt per meter square, and the average transmutive absorptivity factor is 0.85. So what is the actual flux reaching onto the absorber plate will be your product of these two values. So the 950 value is what's coming onto uh, cover glass. From there, only this much has been transmitted. So transmitted absorptive product is 0.85. So this is the actual value going on to your absorber plate minus your overall your heat loss for loss coefficient is 6.2 plus zero point 0.8, right? So this will be 7 into your inlet fluid temperature was, your inlet fluid temperature was um, 50 degrees Celsius, and ambient temperature is 20 degrees Celsius, right? So this will be 50 minus 20, right? Also, you will solve this, your useful heat gain will be 806.6 watt. Now we have calculated the useful heat gain. From here you can calculate the instantaneous efficiency, right? So QU already calculated, it's 806.6 watt. From there you can calculate the instantaneous efficiency, which is Q useful upon your input. Input your the flux coming onto your collector area, right? So it will be your 806.6 upon your incoming solar flux was 950. Note that the area here is taken is for the collector, it's not for the absorber plate, right? So now the area will be your uh, 1.1 into 2.1. Okay, so the 2.1 was the length and 1.1 was the uh, width of the your collector, right? So if you solve this, your instantaneous efficiency will come to be 0.368. Okay, so now we have calculated our performance parameter in terms of efficiency, right? What else we can calculate? We have calculated the useful heat gain. We have calculated the instantaneous efficiency. What else we can get is the outlet fluid temperature. Okay, that also we can calculate. How we will do that? We know the QU value, useful heat. That is actually utilized to heat the heat the air, right? So that will be MCP delta T. Okay, so it will be MCP change in temperature. So this is at outlet and this is at inlet, right? So if we'll put the values, so this will be 200 kg per hour, so it will be 200 kg per second, right? Into your CP is 1.005, it's in kilojoule, right? Kilojoule per kg per Kelvin. And then your TF naught is the unknown term, and inlet temperature we already know, it's 50 degrees Celsius, right? And this is equal to your 806.6, right? So if you'll solve this, you can get the fluid outlet temperature. That will come to be, then this value will be 64.45 degrees Celsius. So we have also now calculated the fluid outlet temperature. What else we can calculate for this given solar air heater? We can also calculate the uh, drop in the pressure also. So if you remember, for that we have to calculate the friction factor, and from friction factor we'll calculate the change in the pressure, right? So the friction factor, if you remember, the for to calculate the pressure drop in so air heater, right? So for that you need to calculate the friction factor. So the friction factor F was given by point the, so this is the empirical relation uh, for the Reynolds number. So if I will show you, so just you can correlate. Okay, so okay, if you want to calculate the pressure drop in a parallel duct for fully developed flow with the smooth surface, we have this Nusselt number formula, and the dimensionless pressure drop in the duct is given by the Blasius equation. The Blasius equation is used to calculate this friction factor, and uh, for the Reynolds number, this the friction factor is already given, and the pressure drop corresponding to that friction factor is given by this equation. So just to correlate, I have shown this. Okay, so now the friction factor you can calculate. We already know the Reynolds number, so it will be 0.079. Reynolds number was uh, 5515, right? So Reynolds number was 5515 to power minus 0.25. This value will be, this value will be 0.009167. Okay, the friction factor. Now we can calculate the pressure drop. So the pressure drop will be delta P, right? This will be your 4FL V square, um, and 4 rho is also there upon your 2 into equivalent diameter. So we'll put the values for friction factor. We know the value 0.009167. Your density was 1.077, right, for air at 55 degrees Celsius, and your length was 2 meter, right, and your velocity was we have calculated the velocity. Okay, so the velocity was 3.439, right? The average velocity was 3.439 upon 2 into your equivalent diameter was 0.0296, right? So we can calculate the pressure drop also. So this will be 15.78. This will be Newton per meter square. So I have solved this question so that basically uh, this is the whole solution. Very lengthy problem, but it incorporates all the important performance parameter of a solar air heater. So the question was to calculate the performance of a conventional solar air heater. What we have seen is how to approach this type of question. What are the important parameter that you have to look for? What is the important formula that you have to remember? What are the important assumptions that you have to mention? So for this question was nutshell in itself, giving all the important factors that you have to remember for a solar air heater. So we have calculated the average velocity, the Reynolds number, then we have calculated your heat transfer coefficient, the equivalent heat transfer coefficient, then we have calculated your collection efficiency factor, your FR factor, and then from there we have calculated this useful heat gain. Once we have calculated this useful heat gain, we can easily calculate the instantaneous efficiency, the change in temperature or your fluid outlet temperature, and then we can also calculate the pressure drop. Okay, so this is all for the solar air heater. If you have any doubt, you can ask right now also, or you can ask in the next lecture also, or you can ping, or you can just write your doubt in the swam portal also. Hope this question is clear. Any doubt in this particular session? Any doubt? Okay, so um I will end this session. I hope there is no doubt. If you have doubt, you are always welcome to ask in the next question, next session. So I will end the session for this live session. Okay, and hope this session was useful to you. We'll meet in next session. So thank you all for listening.